أخباركم يا شباب؟ I received some submissions for the homework, but not many, so I'm expecting some questions. If you have questions on the homework, we can address these now. No? Okay. Okay. Made the announcement for the midterm, inshallah, with all the pages. So let's see if you have any questions regarding the midterm. Material, the way it's going to be conducted. No.
What do we need to set up for the exam?
Just like the quiz, Teams and Blackboard. The exam is on Blackboard, and we'll be seeing each other on Teams.
Okay.
Equations will be there. You don't need to worry about the formula sheets, just like we had in the quiz. It might be a different setting, but it will be there. You just have to know which equations to use. But the video cam has to be working all the time because that's a midterm exam. It's not a quiz. So it has to be working. It's going to include problem solving, true, false, and so on. Next Wednesday, inshallah, we're going to have like a sort of a revision session, only problem solving in preparation for the major, for the midterm. So that's what we're going to have on Wednesday. So Wednesday class is very important in that regard.
Will we be able to go back to the previous question?
No, you will not. No, you will not.
Can you try to think about it at least? Because sometimes in order to save time, we just need to skip and go back to the question after we finish. Especially the time is going to be tight.
Yeah, but sometimes think of it from the other side. Some problems we can do this, but some problems are lengthy, so I have to divide the problem into pieces. Now, in order to help you and not to lose all the problem grade because of a mistake at part A, for example, I have to give you the final answer of part A before you go to part B. So in this type of problems, you cannot go back and change. Okay, but in other problems that are totally separate, yes, we can do that.
Okay.
So let me see how I will do it for that part. We can divide two parts or something like this.
Okay, thank you.
Okay. Any other questions regarding the midterm?
Doctor, can you send the formula sheet to us so when we study for the mid, we can practice?
Okay, fair enough. Okay. Since we have many of them, I will be sending them. Before Wednesday, you are going to have it. And we are going to use it on the revision that we are going to have on Wednesday. So we'll practice using it. Okay. Other questions? Okay. So today, inshallah, we are gonna finish our steady flights. Last time we talked about the required thrusts. Today we are gonna talk about the power as well as the speeds, maximum speed and minimum speed. So power required, the available power, the minimum speed, and the maximum speed. So as you have studied in several courses, the power is the force multiplied by the velocity in the direction of motion. In our case, the force we're talking about is the thrust required. So that's the required thrust. And the velocity, of course, is the same as the free stream velocity v infinity. If you multiply these two quantities, you will get the required power of the aircraft. Now, units of this power would be, of course, the watts, which is joule per second in the SI unit. But it will also be a different unit if you use the British unit. It will be the foot per second, that's the speed, and pound, that's the force, pound force. So foot per second multiplied by pound, the unit is typically called foot-pound per second. Now that's a nasty unit. It's not a very good unit to work with. It's a small value. It has a small value. Typically, engines are rated by the horsepower. It's a bigger unit than the foot-pound per second. A horsepower is 550 foot-pound per second. Now, why do I have to worry about the British system? Because in many cases, once you graduate, you will be using British units as well. Okay? So it would be wise to know this conversion factor. Converting from foot-pound per second to horsepower is 550. Okay. So let's try to calculate this required power for an aircraft. Do we have what's wrong with V and TR? We can use them. Yes, we can use them, but to solve problems, not to design. You don't design using the speed or the thrust. We design using stuff like airfoil, CL, CD, wing area. These are the design parameters. So I need to replace the thrust required as well as the speed by some design parameters. Well, we have that. We already done that. We'll just substitute for them. The thrust required can be found from the drag, because thrust is the drag. And drag can be found from the lift by the drag polar, CL over CD. And the lift can be found from the weight. So at the end, I can replace TR by W over CL over CD. Now, if you look at this, I will give you a few seconds to realize that this is actually TR. Because CD down here is like CD in the top. So CD over CL is drag over lift, but the lift is equal to the weight, so they will cancel. So the drag is equal to the thrust. So this is TR replaced by some design values, the drag polar. Also the speed, V infinity, can be found from lift is equal to weight, 1/2 rho V squared, blah, blah, blah. And we got that expression before, V equal 2W over rho SCL. Where did I get this from? From the weight is equal to the lift, and the lift is 1/2 V rho square SCL. So substituting for V infinity, substituting for TR, I will get the required power in terms of the weight, it's here and here, CL over CD, it's here and maybe another CL here. So when you multiply the terms together, it will be root square 2W cubed CD square rho SCL cubed. Now this expression is very important because it tells me in design where typically W will be fixed, wing area will be determined at the beginning, the ratio of CD square over CL cubed under root square is directly proportional to the required power. That means if you have a bad design with a high CD and low CL, you will have to pay the price by having more power required. If you want to have a design with the minimum power required, then you have a design with the maximum CL to the power 3 over minimum CD to the power 2. Not CL over CD, no, CL3, CD2, and all under root square. That means CL3 over 2 and just CD. If you can maximize this ratio, you will minimize the required power. Now, that ratio changes with the airfoil type. So if you want to pay to spend the minimum power, you will have to pick an airfoil with the maximum of this value. CL3 over 2 over CD. And I can get this value from the drag polar because I have an expression for CD. It has it's a function of CL. So I know this as a function of CL. Okay. So that would be the required power in this case. That's why this value is very important. CL3 over 2 over root square CD over CD. Okay. Let's see this in action. For the Gulfstream 4, the aircraft that we have been using since the beginning of this chapter, calculate the minimum power required and the velocity at which it occurs. Velocity, where is the velocity? There is no velocity here. Where is the velocity? He's asking for the minimum power required. Well, that's fine. I will get it from here. The velocity at which it occurs. How do you find that velocity? Where is the velocity in the equation? Well, the velocity is actually related to CL. If you use certain CL, then the velocity is directly related to that CL. In order to fly at this CL, you have to fly at this speed because they are related by the lift. Okay. So we want to calculate it and compare it to the graph provided by the manufacturer for the aircraft. Okay. So let's see, what do we have? All I have to do is I need to calculate this. So I need this ratio. Now, we know everything about the aircraft from the previous examples. Example 5.1, we know that it's flying at 30,000 feet, so we know the density. We know the weight of the aircraft. We know the wing area. Probably you are familiar with the aircraft right now. And we were given the drag polar of the aircraft. That means we are given CD naught and K. The drag polar is 0.015 plus 0.08 times CL square. So I have that drag polar. So we can find the maximum of CL3 over 2 over CD because I have CD as a function of CL. Now, you can do this in several ways. I can differentiate, get the maximum. I can plot. I can use Excel sheet to plot and get the maximum. In both cases, the maximum of this value turned out to be 10.83. Now, how do I get the value? Well, I put some CL, put a value of CL, let's say 0.5. Put 0.5. I will get CD from the drag polar, and then I have the ratio. I put 0.6, I get CD, I have another ratio. I look at them, I pick the highest one. This is one way to do this. The other way is that I have CD as a function of CL. So if I differentiate, equate to 0, I will get the maximum point. Turns out to be 10.8. So 10.8 in here, that's CL power 3 over CD, but the equation of required power is CD over CL, so I just have to invert it. So inverting the value and squaring it turns out to be 8.52 times 10 to the minus 3. Okay, square, because under the root square, I need C square over CL cubed. So putting them in here, that 8.5 times 10 to the minus 3, all the other parameters we have giving me a power of 2.8 million foot-pound per second. Again, we don't have a feeling or appreciation of this value. We typically feel of the horsepower. So I need to convert this to horsepower by dividing by the 550. 2.8 million divided by 550 gives me 5,091 horsepower. So in order to fly this aircraft at this altitude, the minimum with this speed, the minimum required power is 5,091 horsepower. That's huge. This is the power generated by about maybe 50 aircraft, 50 car engines. Okay? So that's only for cruise. This is during cruise. For takeoff, it will be higher. Okay. Let's see if we have any questions in the example.
Doctor.
Yes.
We find CL, we put any number for CL, you told us, or equated zero.
Yeah, let's see. If I ask you, I want to find the maximum of this. Remember, CD is a function of CL, right? What is CD? It's 0.015 plus 0.08 times CL square. So this whole thing here will be a function only of what? Of CL. Do you agree?
Yes.
Okay. So since it's a function of CL, I'm asking you, what is the maximum of this function? As if I'm giving you Y and I'm asking you, what's the maximum value? I have two ways to do this. Either I plot that Y and find the maximum. So how I'm going to plot it? I will put CL here, whatever value. I will plot it between, for example, 0.1 and 1. I will put a value of CL here. I will put the same value of CL down here because CD is a function of CL. So I will calculate CD for that CL. I will calculate the ratio and that will give me a number, maybe 8. Then I will try CL of 0.2 here and here, maybe 8.5, and so on. I will plot the whole function and I will get the maximum of it. Turns out to be 10.8. Now that's the graphical way. Now, that's not necessarily the best way. The best way to get the maximum is to differentiate that function, right? So I will put CD 0.015 plus 0.08 times CL squared and get me the maximum of that function. So you will differentiate and you equate to 0, you get CL and you will get the function to be 10.8. And I left this for you to do and get back to me if you can do it. I will do it in detail on Wednesday when we do the revision session. Because that's a math thing. You have a function, I'm asking you what's the maximum value of that function. Okay, so take the CD out and replace it by 0.015 plus 0.08 CL squared and get me the function, the maximum of that function here. Okay. Check if it's 10.83, yes or no. And at which CL, by the way. You see, I didn't tell you at which CL this is going to happen. Okay. So either plot it or differentiate it. Okay. So we use the drag polar. Okay, so that's for the required power. Then comes the next question, the available power. If you need this power to fly, what's the power provided by the engines? Are they sufficient or not? So that's the question of the available power. Luckily, we don't have to do anything in here because we already did this in the engines chapter 3. Remember back then, we looked at the power available from an internal combustion engine. This is the propeller powered aircraft, or from a turbojet or a turbofan. We found that the power from a propeller driven aircraft did not change actually with speed. It was constant with speed. If you go back to the lecture 3, when we were talking about the chapter 3, we got that there, we made that list. So it didn't depend on the speed, it depended only on altitude. It changed the density because the higher you go, the less air that will get into the engine, the less power that will be generated. And back then, there was a formula relating that power to the density. As the density decreases from the sea level density, the power available will decrease from the power available at sea level. Okay, and depending on the reduction, will have a formula, and was found then that that value of about 0.7 was a reasonable value for the standard atmosphere. That's not a new equation, it's from chapter 3. The same goes for the turbojet or the turbofan, and we actually solved a problem on something like this back then. The available power changed with the density in here with a certain function, and M changes depending on the model of the engine that we have. Typical value would be like 0.8, and of course it has to be provided. Now this is the available power from the engine, or the available power for the aircraft. Now we have to mention something. This is the power that the engine is going to provide to the air, but it's not the power that's generated by the engine. The power generated by the engine, P, has to be slightly more than this to account for the losses and the efficiency of the propeller. So if you need an available power to you of 100 horsepower, then the engine should generate a little bit more, maybe 110. And in this case, the efficiency of the propeller would be 100 over 110. Okay. Typical efficiency of propellers would be around 0.8. Again, that's in a course like this, in an analysis part, that has to be given to you. But to know it, efficiency of propellers around 80%. So if the engine generates 100 horsepower, the propeller will deliver 80 of that 100 to the air. Okay. Now, why the required power and the available power are important? Because we will start to look at this velocity regime of the aircraft. What does that mean? The aircraft can fly at this velocity and it will need that power. This is the required power from the equation that we had in here. For every velocity, where is that? For every velocity, I have CL and I have required power. So for every velocity, I have required power. Another velocity, another power. There is a velocity where the minimum required power, you see, the one that we had with maximum CL3 over CD2. Another velocity, a different power, and so on. So the airplane can fly at any point here, at any velocity in here, as long as this required power was less than the available power, because the engine can provide me that much, but I only need this. So I can fly here. Engine provide me that much, I need this. I can fly here. Until the two curves meet, beyond that, the airplane cannot fly. You cannot fly at Vmax plus 1 kilometer per second. Why is that? Because at this point, the engine can barely provide enough power to maintain a steady and level flight. So the maximum speed is determined by the intersection of the available power and required power. Remember, for a propeller-powered aircraft, the available power was unchanged with speed. That's why it's a straight line. It was constant. So when it's equal to PR, that's when we have the Vmax. That means if I take PA from here, the available power, equated to be required from here, if I equate these two expressions, I will get the maximum speed of the aircraft. The speed at which this ratio will come, that will be the maximum speed of the aircraft. This is true for propeller aircraft, and it's true for a jet aircraft. The only difference in here is that the power available for a propeller-driven aircraft does not change with speed, but for a jet-powered aircraft, it does change with speed, of course, because the power is the force multiplied by the velocity, and the force is coming from thrust mass flow rate times velocity, so it's a function of the velocity. So again, this is the maximum speed. So by equating the two powers here, or the two powers here, I will get the maximum speed of the aircraft. Okay. So that's one end of the flight regime, maximum speed, how fast the aircraft can fly. This is just like your car. The maximum speed of your car is determined simply by the horsepower of the engine. More horsepower, more speed. Okay. If this horsepower goes up, the intersection will be higher here, and the maximum speed will be higher. Any questions? Okay. Now let's look at the other side of the velocity regime. The aircraft can fly here, 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 here for jet powered, or here, here, here. But how slow can the aircraft fly? Where should I stop? Should I stop here, or here, or here? Why does the curve start from here, whereas the curve here intersected and when? Well, the reason for this is that the minimum speed of the aircraft is determined by two factors. One of them is aerodynamics. The aircraft cannot fly below that speed, otherwise it will stall and fall from the sky like a rocket. Or maybe it's determined by the available power and the required power. I cannot fly beyond that here because in this range, the required power is more than the available power. So I will not be able to cross that point. This is the minimum power in this case. I cannot go slower until stall occurs. I cannot go slower because the required power is more than the available power. So for this curve, for example, this is the minimum speed, minimum velocity. It's determined by stall. For this curve, this is the minimum speed. It's determined by the power requirement. And before we design the aircraft, I will not be able whether it's going to end here or here. It depends on this value, whether this value is the intersection before or after the stall. Here is stall and here is the power requirement. Okay. So we will study this. We will study how to calculate the minimum speed. Now I need to ask a question here. Why is the minimum speed important? Let me put it in another way. If I have one design that gives me a minimum speed of 100 knots or 100 miles per hour, and another design gives me a minimum speed of 60 miles per hour, which one do you think is better?
I think, Doctor, for the takeoff.
Yeah, so it is the 60 for the takeoff. You both are right. The lower speed is better because it will mean shorter distance for takeoff, shorter distance for landing. Okay, that's what's called improved performance of the aircraft. Okay, so the minimum speed is important, and the lower the minimum speed, the better. But we cannot go below the stall. We cannot go below the part where we have high power required. So let's study both. Let's study this point as well as this point. Let's study first the stall point. The stall, that means this point, the aerodynamics part. Can I determine the stall speed of the aircraft, the minimum speed? Yes. Since speed is related to CL by lift, if you increase CL, V will go down. So if you use CL max, that will be the minimum speed or the stall speed. Beyond that, you cannot increase CL because it will fall down. So that would be the stall speed of the aircraft. So if you use CL max, you will get the stall speed. So that's the equation. It's not a new equation. We just put here CL max. What about the power required? Well, in this case, it's not the power that determines the minimum. It's actually the thrust. It's, yes, the intersection, but below that curve, you need more force, more thrust in order to move the aircraft straight and level. We had an expression for the velocity that's required at this intersection. Remember, we had it before. Since this intersection is parabolic, last time, we found that the speed can be determined from a parabolic equation. That means the roots of a parabolic equation, which you know from math, of course, to be minus b plus or minus b squared minus 4ac over 2a, the solution of a quadratic equation. And we used the plus last time because we were interested in that intersection. But if you use the minus sign, I will be interested in the other intersection because I have two solutions, plus and minus. So the required minimum intersection here means I need to use a minimum sign in here, a negative sign in here. So V max, if it's a plus sign, V minimum, if it's a negative sign. So now I will have two expressions, one determined by the thrust and power requirement, the other one is determined by stall. Let's say this one is 60 miles per hour. This one with a minus sign gives me 80 miles per hour. What would be the minimum speed of the aircraft, 60 or 80? Again, the question. This equation here tells me the aircraft will stall at 60 miles per hour. This equation here with the negative sign, of course, when I use a minus sign, will tell me that the intersection will occur at 80. So what would be the minimum speed of the aircraft?
80, Doctor.
80, of course. 80, because 60, that would be here. Okay, that's fine. But the airplane will not be flying here because the required power and thrust is more than the available. So I will not cross that. So it will be the 80. So we should calculate both of them and use the highest of them. Okay, the highest of them is the one that's suitable. Okay. So now to the last part before we solve our problem on this issue. We agreed that I need to calculate V stall, I need to calculate the V minimum from here, get the power. Can we calculate them? Yes, typically I would have the weight, I will have the thrust, area, CD naught. I can do this one, no problem in here. But for the stall speed, IW over S, CL max. I need CL max. Where would you get CL max? If I give you a problem and ask you calculate the stall speed, typically, where do you go to get CL max? Don't tell me the drag polar. because it's not CL over CD or anything. I just need what's the maximum value of CL. Where do you look in order to get that value?
Angle of attack.
Yes. So in the airfoil data, you will have CL versus angle of attack. So we will go to whatever airfoil we have for the aircraft. You will look for the curve that relates CL over alpha, and you will find where is the maximum point that will be CL max. Okay. Now that would be high or good enough for cruise, but for takeoff and landing, sometimes we need more CL than this. Okay, so CL max is limited by the fact that we have a stall in here. So that's why stall is important, because it prevents us from going beyond that value of CL. If there was no stall, I can go along the straight line, get more CL, get lower speed, and that's good. Lower speeds means everything. I can decrease the takeoff distance, I can have better wings and so on. So stall is important. So when the wing stalls, that means it has a higher angle of attack than the maximum speed. What will happen is that the flow will separate from here and it will circulate without generating lift. If you look at the same airfoil, but from the top, I will see the wing as a rectangle. That's the wing that we have in here. It's a rectangle. At a high angle of attack, air is coming from here, and you can see the velocity contours. Ideally, I should not see any of these. Air should go like in straight lines like this, streamlines. But what will happen is that air separates and starts rotating. All this part is not generating any lift. All this part is not generating any lift. So it stalls. That's why the curve actually goes down in here. CL goes down. Okay. So in order to improve this at low speeds, we need them for takeoff and landing and maneuvers, sometimes for military aircraft. Engineers looked for ways to increase the CL without stalling the aircraft. One way was to change the airfoil. Now that's a good choice. Instead of having an airfoil here that stalls at this value, let's pick another airfoil that stalls at a higher value. But the aircraft cannot change airfoil while in flight. So the other way, let's change the airfoil camber while in flight. So that's where the whole idea of flaps came from. So a flap is there so that when it's deflected, the wing airfoil will have more camber and then thus will have more CL. So flaps definitely increase the camber of the airfoil. The more sophisticated flaps that you have that can change the camber more, the more in CL you are going to get. So if you have a wing with no flaps, maybe the CL will be like 1.4. That's the CL maximum at stall, 1.4. But if we have a plain flap, simply deflecting the trailing part of the airfoil, that will increase it from 1.4 maybe to 2.3 or 2.4. That's the plain flap. If we have a split flap, that will increase it even more, maybe to 2.6. Now the camber increased in here and I'm getting more lift from the upper surface. If we have a slotted flap means we have the deflection. Yes, we are increasing the camber, but also the chord here is increasing. It's moving outward. So the CL will go up more. We have double slotted, we have triple slotted. These are the types of lift devices that you see on the trailing edge of any wing on your aircraft when you are on board an aircraft while the aircraft is landing. You see all these extending from the back, just simply increasing the camber in here. Increasing the camber means more CL maximum. So flaps are called trailing edge devices because they are attached to the trailing edge. Now, they are good in a sense that they increase CL. So you see flaps increase CL, but they are bad in a sense that when they increase CL, they tend to decrease the stall speed. So here is an unflapped wing, for example, no flaps. This is the regular wing. Here is the CL maximum, and here is the stall speed, stall angle of attack. When you expand or extend the flap, the curve will not be this one, it will move to be that one, because you have changed the camber. It's as if it's a different airfoil. The good thing is that we increase CL max. The bad thing is that we decreased the stall angle of attack. It doesn't stall here, it stalls here. And that's bad, because that means the aircraft cannot go slower. So flaps improve CL max, they decrease alpha stall. In order to avoid this bad effect of flaps, engineers have resorted to what's called the leading edge devices. Leading edge devices, think of them are flaps, but in the front. They simply bend to increase the camber, or bend and move to increase the camber, increase the chord, and increase the energy of air going in here, in between. Sometimes they are called slats. Sometimes they're called leading edge flaps. Now, the good things about slats is that they increase the angle of attack as well. So if you have an unflapped airfoil and you have a slat, it will increase both CL and alpha as well. Not as much as the flap, but it will increase. Okay, so slats are all good. You get good CL, you get good alpha. Flaps are not that good. Good CL, but bad alpha. Sometimes they are being used in combination. I can use a slat plus a flap, just like this one in here. Double slotted flap plus a slat. You get the good CL, you get the good CL. You have bad alpha, you have good alpha, they will cancel each other. That's why we will have leading edge as well as trailing edge high lift devices. Slats and flaps together are called high lift devices. Why high lift? Because they increase CL. Is this clear? Any questions so far? Okay. So how much do they add CL? I need CL max in here, Should I read it from a curve? Not really. We can have it like in a table, something like this, which is the typical values in the industry. A plane flap, which is simply bending the trailing edge. This is the simplest of the flaps. That is deflected at 20 degrees when the aircraft is taking off, will give me a CL max somewhere between 0.4 and 1.6, maybe 1.5. Why a range, not an exact value? Because it depends, of course, on the airfoil. But for most airfoil, it will be between 1.4 and 1.6. The same flap, if deflected more at 60 degrees, it will give me more CL, between 1.7 and 2. When do I need to deflect it more? During landing, because I want to go slower, I need to have higher CL. So that's for the plane flap. For a single slotted flap, I will have different values, but more than these. See, the second row is more than the first one. For a Fowler flap, I will get even more. Double slotted Fowler, double slotted, triple slotted slats, that will add even more in here. So this table gives me the industry standard for the CL maximum when you have deflections of any of these high lift devices. Remember, as much in takeoff as well as landing. Do you know why? Why deflections in landing are more than deflections in takeoff? Why this deflection in landing is more than that in takeoff?
Because of the angle of the air.
What do you mean by the angle of air? We don't have an angle called angle of air. We have angle of attack. We have the angle of the aircraft. Angle of attack. And why would the angle of attack be different in takeoff and landing?
Doctor, to reduce the speed?
Yes. So why would the speed in takeoff and landing would be different? That's a correct answer, the speed. My question is, why is the speed in takeoff more than that in the landing? In the takeoff, it's more, so the deflection is less. Why is that?
Landing, we need to reduce the speed.
Maybe because we have the plane heavy when we at takeoff, and it's less than in landing.
Well,
because
that's the plane is heavier, of course, in takeoff than landing, but that's not quite the reason, because remember, we're talking coefficient, CL. I'm talking about why CL here is more than here. CL does not depend on the weight. When we talk coefficients, we have taken the weight out.
Maybe takeoff, we need
for
speed and
Yes, in takeoff, why do I have to go a little bit more than the stall speed? In landing, I need to land the aircraft almost exactly at the stall speed to have a smooth landing. So I need to stall the aircraft when it's touching the ground. So I have to go as slow as possible and stall the aircraft when it touches the ground. So almost it's the stall speed. Whereas in takeoff, I can take off at stall speed to have a very smooth takeoff, but that would be very unsafe, because aircraft is airborne. If the speed is slightly changed, it will fall from the sky. So in takeoff, aircraft will take off at 1.1 times VSTOL, more than the speed stall, 10% for safety. So if you go faster during takeoff by just 10%, that means you need less CL. And if you need less CL, that table tells me I need less deflection. Okay, so that's why I take off at 20, I land at 60, because here I have to be slower for smooth landing, and I'm not worrying about stall because the aircraft have just touched the ground. Let it stall when in the ground, but here the aircraft is going up. You cannot stall the aircraft when it's going up. Okay. Any questions? Okay. So let's see a problem. Let's solve our problem. Calculate the minimum velocity of the Gulfstream aircraft at sea level based on the two conditions we talked about. What are the two conditions we talked about? The low speed intersection of the thrust available curve and the stall velocity. And we agreed whichever is higher will be our minimum speed. So we need to calculate both speeds, stall velocity as well as the intersection of the curves. It's telling me the airplane has a single slotted Fowler flap and the sweep angle of the wing is 27 degrees 40 minutes. And now I have to see, why do we need the sweep angle of the wing? We didn't see a sweep angle anywhere. We didn't see it here. We didn't see it here. What is the other velocity? Here, there is no sweep angle of the wing. Well, we saw the sweep angle in the wing in here, embedded in that table. Now, why do we have to worry about sweep? Remember, this table doesn't know whether your aircraft will be swept or not. It tells me this will be CL if this is the deflection, if you have a wing that's unswept, rectangular wing. But if the wing is swept, that means the aircraft has a wing that doesn't see much of the air, it's bent backward. Then you should expect that CL to go down a little bit, right? If there is no sweep, that means the wing is completely rectangular, then that will be CL between 1.4 and 1.6. But if there is sweep, then the air will not see the full wing, it will see just a projection. So that's why we have to multiply by cosine the sweep angle here. So if the wing is swept, then this value will go down by cosine the angle. Is this clear? Zero sweep means cosine 1 means you use the 1.4 to 1.6. But if you have 10 degrees sweep, then I will take whatever value from this table and multiply it by cosine 10 degrees. That's why we were given here the sweep angle is 27 degrees 40 minutes. So let's calculate the speeds. Let's go on with the minimum speed. This is the speed from the intersection of the curve with the minus sign. I'm calculating this 0.3 here. Same equation as Vmax, but with a minus sign. So we are using it. Minus TWWS. We have everything in the aircraft from the previous examples. We didn't calculate them. They are data. They are just provided. W, the weights, wing area, thrusts, CD, K, everything. So the minimum speed here turns out to be 117 feet per second. Below this speed, the aircraft cannot fly because the engines will not give me enough thrust. Now, from the stall, the other equation, the stall equation, Vstall and CLmax, I need to put CLmax in order to get Vstall. Well, CLmax from the table. The problem says it has single slotted Fowler flaps. Well, single slotted Fowler flaps during landing, because that's where I have CLmax, not takeoff. Takeoff, we take off a little bit more than the stall speed. In landing, it will be between 2.5 and 2.9. So it is wise to use maybe 2.7, something in between. So CLmax over cosine, that's from the table, is 2.7. This value is from the table. And we said it was going to be multiplied by cosine the lambda because of the sweep, which is 24 degrees something, or 27 degrees. So the 2.7 multiplied by the cosine will go down to be 2.39. So the CLmax is 2.39. We lost about 0.2 of lift because of the sweep. Sorry, not 2.2, 0.3 maybe, because of the sweep. Okay, so CLmax is 2.39. Put it in the equation, get a stall speed of 164. The airplane cannot go below this speed because it will fall from the sky like a rock. So which is the minimum speed of the aircraft? It is the maximum of these two. It is the 164. That means the airplane will stall before the curves intersect. That means the curve will be something like this case. The airplane will stall before the two curves intersect. So that's the minimum speed. In other aircraft, maybe it will intersect before it stalls. And in this case, that will be the minimum speed. Okay. So for our example problem, the minimum speed is 164.5 feet per second, and it is determined by stall. Any questions? Now, when we start do designs in chapter 7, Vstall will not be left to you to calculate. Okay, so it's not like a designer parameter. Vstall is determined by regulations. So here in Saudi Arabia, GACA is the one responsible of putting stall speeds for all categories of aircraft. In the US, it's the FAA. Now, these regulations are very much close to each other in many countries. So, for example, they would say if you have a large transport aircraft heavier than 50,000 pounds in weight, multiple engines, the stall speed cannot be more than 120 miles per hour. If you have a general aviation aircraft, that's a smaller aircraft, the stall speed cannot be more than, let's say, 90 miles per hour. If you have a two-seater aircraft, a very small aircraft, home-built, the stall speed cannot be more than 45 miles per hour. So the smaller the aircraft, the slower is the stall speed by regulation because of safety concerns. Because small aircraft will take off at low speed. So if you allow stall at low speed, that will be dangerous. Okay. Any questions, Yashin? So Wednesday, inshallah, we will be solving problems in preparation for the midterm. We are going to have our exam on Sunday, but I have received multiple requests of putting the exam a little bit later that night instead of 6:30, maybe at 8, because some of you have like conflict with other exams. So I will post that on Blackboard, but if you have a problem with this, let me know as soon as possible. So if you don't have a problem with having the measure at 8 p.m. instead of 6:30, I will delay that to avoid conflict for some of you. Okay, so I will modify the announcement on Blackboard for the exact time. Okay, so I will be seeing you inshallah on Wednesday. Shukran.